Good morning. I hope you can see my screen and you can view me. The topic of my presentation is Q-Rasar versus Qsar, efficient predictions of activity, property, and toxicity endpoints. So I think everybody here is conversant of Qsar, which is a statistical approach of data gap filling. So we collect data, endpoint data from various sources like online databases or scientific articles, etc. And after biological and chemical curation, we prepare our input data. We go for descriptor computation from the molecular structure information using variety of software tools. Then we go for dataset division. This is important because Qsar is a statistical model building approach. So we need to see how good or bad our model is for new or unseen data. In case we do not have sufficient unseen data, we divide our original set into training and test. Training is used for model development and test set is used for prediction purpose. We select important features for the endpoint we are going to model, and then we apply appropriate learning algorithm, which may be regression or classification based. And finally, the developed model is analyzed for their quality and predictability in terms of various quality and variation metrics, depending on the nature of model, whether it's a regression-based or classification-based model. Qsar has found application in a variety of areas, including pharmaceutical science, material science, food science, agricultural science, nanoscience, and so on. Another approach, which is read across, is also used for data gap filling, but this is not a statistical method. This is accepted by regulatory bodies for prediction purpose. It can be of two types, mainly analog approach and category approach. Analog approach is used when the number of source compounds is limited, and category approach is used when we have a sizable number of source compounds. And depending on the similarity, we can fill the data gap by either interpolation or extrapolation. Now, in case of read across, the original similarity consideration comes from chemical structure information, but that is not sufficient according to the rough guideline, read across framework, where we have also to consider the toxicokinetic and toxicodynamic consideration for addressing different issues for uncertainty and confidence of read across hypothesis. And once we are satisfied, considering different scenarios, we can apply a particular hypothesis for prediction purpose. Now, we have developed recently a quantitative read across workflow, which is basically based on chemical read across, where we do not consider the toxicity or metabolic aspects. We only consider chemical structure information. And we apply this read across hypothesis generation based on a set of source compounds. And finally, we predict for a set of query compounds. Now, the source compound list is again subdivided into sub-training and sub-test set in several iterations. And we apply different measures of similarity based on Euclidean distance-based similarity, Gaussian kernel-based similarity, and Laplacian kernel-based similarity. And based on the performance on the sub-test set, which is obtained from the training set itself, we optimize different hyperparameters. And finally, based on weighted average prediction, we go for prediction for the test set compounds. And we check the quality of prediction in terms of various validation metrics, as we do in case of Qsar. Now, we can give one example. Say, for example, if our query compound is bromobenzene, we'll search for its close congeners. Say, for example, these three are the close congeners, and based on our different similarity measures, we will calculate the distance of this particular query compound to the source compounds in terms of distance measures or similarity measures, and finally, we find out the weighted average prediction for the endpoint. Now, whether the non-statistical approach of read across can be combined with statistical approach of Qsar or not, that was explored by Lutfi et al. a few years back, where they have developed classification-based modeling using mainly two similarity measures, maximum positive and maximum negative values. But they have not applied it for regression-based problem, or they have not expanded the similarity measures to other additional descriptors. So recently we have expanded the concept into quantitative read-across structure-activity relationship, where we apply the similarity consideration of read-across and we put it in the Qsar-like framework. So like Qsar, we start from the training set, and that is divided into several sub-training and sub-test set. And then by applying different similarity measure, we develop read-across hypothesis, and we try to find out the optimum hyperparameters and optimum similarity measures based on the performance of the sub-test set. And the chosen set of hyperparameters and similarity measure are used for read-across structure-activity relationship descriptor calculations. So these Rasar descriptors actually compute a set of similarity measures and different dispersion measures, which can be used in association with structural and physiochemical descriptors. And like Qsar, then we apply the feature selection tool, and we can develop model using our chosen method of model development. And after developing the model, we apply on the tested compounds for prediction purpose. So these are the different similarity and dispersion measure. For each query compound, we try to identify its close source compounds up to 10 in number. And then we can calculate the standard deviation of the response values of those compounds and their coefficient of variation. We can calculate different similarity measures like mean similarity value to the closed source compound, standard deviation of similarity value of those closed source compounds, maximum similarity value of positive closed source compound, maximum similarity level to the negative source compound, their difference, and also we apply a concordance measure, which is G. This was actually applied by Wu et al. In a different context, but here we have applied for defining the similarity to either positive class or negative class of compounds. So these are the mathematical expression of defining different similarity and dispersion measure. As you can see, the weighted average response is the activities, CD similarity, Euclidean distance-based similarity function, then Gaussian kernel-based similarity function, which uses L2 norm, Laplacian kernel-based similarity function, which uses L1 norm, average similarity, standard deviation of similarity values, maximum positive, maximum negative, their difference, and concordance measure G. Now this concordance measure G can produce similar value for same value of positive fraction and negative fraction. For example, when it is 0.6 for positive fraction, the value of G is 0.8. For negative fraction 0.6, the same value. So we thought that we need to redefine this concordance measure. And then we came with this modified G value, which gives different values for the same level of positive and negative fractions. So value of GM ranges from -1 to +1. Now, in case of Rasar, when we start with the original chemical features, we apply the different mathematical expression for computing the similarity level. And we consider the nonlinear transformation. And finally, we get a measure that is called RA function that is obtained in a nonlinear way. But this function or descriptor, which we use for Qsar model generation, we can then apply linear framework. So although the final model is linear in nature, but the descriptor we obtain in a nonlinear fashion. And we have seen in many cases, the linear model can also supersede in quality the nonlinear model. Now, only the RA function is not sufficient. For example, here we can show the examples of query and source compounds. This question mark, these are query compounds, and the other notation is the source compound. And as you can see, for the 3 query compounds, the similar source compounds are present, but their response level are not same. And that's why, although their RA function value are same, we need to use the additional descriptors, maybe the original structure and physiochemical descriptors, And there may be different scenarios also. As you can see in the first circle, that represents where the maximum positive value is more than maximum negative. Here, the positive and negative is defined based on a particular threshold, which is here the training set response mean. So any value higher than that, that is considered positive, and any value lower than that, that is considered negative. Now, the second scenario is that where borderline compounds are present. So GM value is 0. So positive fraction is also 0. So the degree of confidence is low here. And in the third scenario, the maximum negative is higher and GM value is negative. Now, the Qsar concept can also be linked with AOP, adverse outcome pathway, by defining the maximum severity value of query compound to different inhibitors for different targets. Those are related to different molecular initiating events. Now, in a very simple form, when we apply the Qsar concept with the framework of 2D Qsar, we can start with chemical data set with quantitative response value. We compute 2D descriptors. We divide the results into training and test. We select features for Qsar model generation, as well as we generate chemical similarity measures from the training set. And then we develop a Qsar model from the training set itself and apply on the test set for prediction purpose. Now, regarding Qsar descriptor calculation, in case of usual Qsar, we compute Qsar descriptors from a particular compound based on its chemical feature itself. And we compute descriptors before division of training and test set in case of Qsar. But in case of Qsar, we compute Qsar descriptors after division into training and test set. And the Qsar descriptors are computed using the training set compound as reference or source. And for the training set also, the Qsar descriptors are computed using training set as the reference. And we optimize hyperparameters using the validation set, which are obtained from training set. There is no dependence on the test set. And after we compute the Qsar descriptors and optimize hyperparameters from the training set itself, we then apply this for the model generation, and the test set compounds are predicted using that particular model. Now, in case of Qsar, in addition to the Qsar descriptors, we can also combine Qsar descriptors with the usual Qsar features like structural and physiochemical descriptors. And the combined descriptor matrix of the training set is subject to feature selection and model development, which is then applied for the test set compounds. Now, I'll show some case studies here. As you can see, this is a modeling of androgen receptor binding affinity. So we started with a set of compounds. After structure curation, we went for descriptor calculation, data pretreatment, data set division, then model generation using usual Qsar descriptors. So this is the original Qsar model that we obtained with acceptable Q-square LO value of 0.68 and Q-square F1 for the external cell 0.58, somewhat low one. And these were the selected 2D Qsar descriptors. Then we went for Qsar descriptor computation from the selected feature in the Qsar set. As you can see, these are the Qsar descriptors: maximum positive, average similarity, G value, and these are the Qsar descriptors. So we obtained 4 individual Q-Rasar models, and then also we went for some Q-Rasar models using some pooled features from these 4 modules. And for the individual Qsar model, these are the plots showing the relative importance of different descriptors. As you can see that in most of the cases, the Qsar descriptors are more important. That is obtained from the bubble size that corresponds to the VIP values. And if we see the relative performance of the models in terms of the MA value of the test set, we will see that the intelligent consensus prediction for the model 3 from 4 model ICP3 that shows the best quality of prediction for the test set. And this is better than the individual Qsar or individual redact of this prediction. Now, in this model, we initially use G, but when you replace this G with GM and redevelop the model, we see there is enhancement of the quality. The Q-square F1 enhances to 0.674. And if we see the VIP plot, initially the G descriptor was here, and GM is obtained as the second most important descriptor. That shows GM is more important than G. Next, we did another analysis where we used 5 different toxicity endpoints, and the 5 endpoints are androgen receptor binding affinity. This is somewhat different from the previous study, because in the previous study, we didn't use RA function. In this study, we introduced RA function. We also modeled acute oral toxicity data, the BART toxicity data, acute contact toxicity data of honeybee, acute oral toxicity data against another BART species, Malamda, and inhalation toxicity data. And using the same kind of workflow, we developed our Qsar model using Qsar descriptors and usual 2-dimensional structure and physical descriptors. These are the plots showing the relative importance of descriptors. In most of the cases, we can see that the Qsar descriptors are present as most of the important descriptors, either the first or among the first few. So we can see that here RA function, here CV activity, and here also the maximum positive similarity. These are present as important Qsar descriptors. Here also we can see the GM into average similarity, and here also GM into SG similarity. These are present as important descriptors. Now, if you compare the Q-Rasar model with the corresponding Qsar model, we can see in all the cases, the external validation quality of the Q-Rasar model here in terms of Q-square F1 is always better than the corresponding Qsar model. Now, the Q-Rasar model is generated from the features used in the Qsar model. We are not using any additional chemical information here, but we are just calculating the different similarity measures, and we are combining the used structural physicochemical features with those similarity measures and redeveloping the Qsar models. And you can see there is significant enhancement of external validation statistics in all the cases. Here 0.77 versus 0.65, here 0.83 versus 0.65, here 0.68 versus 0.66. But one thing should be noted here, in many cases, the R-square and Q-square LO value of Qsar model is somewhat inferior to the corresponding Qsar model. The reason is that in case of Qsar, we calculate descriptors from the particular chemical compound structure or property information. But in case of Qsar, we do not compute Qsar descriptors from that particular compound, but from its close congeners. So it learns from its close congeners, not from the particular query compound. Compound which is in the training set for training set descriptor calculation. So in case of Qsar model is developed by a process of fitting, but Q-Rasar is not developed by the process of fitting only. Some prediction aspect is inbuilt there. And that's why the Q-square LO is somewhat inferior to the Qsar model, but Q-square F1 is always, in most of the cases, it is superior than the corresponding Qsar model. There may be different scenarios. As for example, in this particular case, this is the query compound, and all the close compounds are the positive, and the degree of dispersion is low. In this particular cases, all the close compounds are positive, but degree of dispersion is high. And depending on that, you will see different values of the SD similarity and SD activity that will vary. In this case, as you can see, the borderline compound, query compound, there will be positive and negative closed source compounds. So here the confidence is low, and RA function may be either positive and negative. And in this case, all the closed source compounds are negative, and the dispersion is low. So we get more confidence here. Now, if we compare our quality of model with other machine learning models, okay, I'll take 2-3 more minutes. In that case, we will see the quality of...
No, you have enough time, actually.
Yeah,
you have 30 minutes.
Dr. Roy, thank you for the presentation.
Yeah, no. You have enough time to continue.
I have 10 more minutes, including the question and answer.
Yes, please.
Yeah. Yes. So you can see, if we see the MA value of the tested compounds, The MA value for the tested compounds is lowest in case of MLR. For the other machine learning methods like linear SBM, SBM, random forest PL, that is regression, and also PLS, the MA value are sometimes higher. The MA is here. This line represents MA, sometimes higher or close to MLR. But in these 5 examples, always MLR has emerged as the most that is a promising method of model development using Qsar descriptors. Qsar descriptors are obtained in a non-linear fashion, but final framework of model generation is linear in this case. This is a SHAP analysis of the model generated, showing that Qsar descriptors are at the top, as you can see, RA function in the training set and also test set here in the data set 2. The negative error similarity in the top. In this way, we can see in most of the cases, Qsar descriptors appear in the top of the in the sequence of order of importance of different descriptors. And these are additional cross-validation by repeated 5-fold cross-validation, etc. I'm not going into details. And one more case study for cardiotoxicity, we have used the similar fashion of workflow. And this is a disease plot that identifies prediction confidence outlier. In the y-axis, we show the difference of the observed activity or response values of closed source compounds, and the bubble size represents the difference of similarity. So any compound that appears higher with higher bubble size is expected, but any compound which appears in the top, that is more than 1 log difference, but the bubble size is smaller, that means difference of similarity is smaller. That is a point of concern. So these compounds are actually outlier. We can identify outlier in this fashion in the test set compounds or query compounds. This is the PLS Q-Rasar model developed here with good statistics. And you can see from the variable importance for Qsar models, Qsar descriptors are more important. And this is the scatter plot identifying some outliers. And this is the comparison with other machine learning methods. And we see the PLS method is the best here in comparison to other machine learning methods like random forest or gradient boost, data boost, or regression. We have also applied it for classification with good performance, and also developed a tool for prediction of the endpoint value. We have developed several tools, Java-based tools for quantitative read across optimizer for the hyperparameters, Qsar descriptor calculations, and machine learning regression. And we have applied this Qsar for different other property endpoints like specific surface area of perovskites, power conversion efficiency of organic dyes, then other toxicity like skin sensitizer classification and regulation-based problems, are also for binary organic pesticide mixture in honeybee toxicity, and also for nano toxicity modeling. So finally, we conclude that these studies report some simple, interpretable, and reproducible Q-Rasar models with good external predictions, which are superior to corresponding Qsar model without using any additional chemical information. From the most of the studies, we have found that RA function, GM, and average similarity appear as the most important similarity-based descriptors. The Qsar concept and the tools have been developed by my PhD student, Arko Prabhu Banerjee, whom we have already heard yesterday. More about Qsar are present in this site, and the tools are available freely from this site. And other research groups have also worked with Q-Rasar, and their papers are listed here with link. And we received funding from ACRB and Life Science Research Board, DRDO. This is our recent book on Qsar and machine learning approaches. Finally, thank you very much. If you have any questions, I'll be happy to answer. Thank you.
Dr. Roy, thank you for amazing presentation. Dear colleagues, we have any time for question. Please ask.
I don't see any question in the chat anyway.
Yes, I don't see too. I see good presentations here. That's all. I agree. Absolutely.
Thank you. So the different case studies we have done with Qsar descriptors, and the corresponding papers are already listed in our site. Or if anyone is interested, one can go through those papers from our lab and from different other labs, and all tools are freely available from our site. So I invite everyone to check, to try our tools for calculation. And this Qsar concept is not limited to a particular kind of descriptor or particular modeling strategies. One can use 2D or 3D or any kind of descriptors. Only thing is that the chemical information is encoded by the corresponding 2D or 3D descriptors, and from those descriptors, using the selected feature information, one can calculate different similarity measures and then go for Qsar model development. And for Qsar model development, one can do the usual linear MLR-like model development, or one can go for machine learning like random forest SVM or any other method of modeling, depending on one's need and choice. One can use regression-based, one can use classification-based modeling. So everything is open. Only thing is just comparison with the corresponding Qsar using the same level of chemical information, whether we can enhance the external predictivity or not. And from the Qsar modeling is different in that respect that we are not calculating Qsar descriptors from the particular query compound structure or its chemical information. Instead, we are calculating Qsar descriptors from its close congeners. So as it tries to learn from its close congeners, so that prediction aspect is inbuilt during model development. So that's why we call it prediction-inspired modeling, prediction-inspired modeling. And it is application of read-across in Qsar. That's why we call it read-across structure activity relationship, or Qsar.
Thanks. Actually, I have one question.
Yeah.
What do you think? Can we use our application for predict selectivity index, for example, antiviral compounds?
You say you want to use it for calculation of selectivity index for a particular kind of virus, or means against different targets. Would you elaborate more?
Of course, if we learn about biological targets.
Yes, that can be done. I have shown one, I think, one particular slide where we can work with different targets. So you can do it, that is called data fusion Qsar. So one can do Qsar using multiple targets. Not only with particular target, one can do with multiple targets. And there you can do the selectivity analysis. I'll go to that slide, I think here. Yes, you can see target 1, target 2, target 3. You can work with different targets, and you can do multi-target type of Qsar development using, say, modeling method like random forest, or if you have enough data, if you are using some neural network or deep learning, if you can use deep learning methods. So you can do multitask model development. So it is possible to obtain information with respect to selectivity against different targets.
Interesting. Can I try? Can I submit it?
Yeah.
Okay. Thank you. Thank you. So very interesting.
Thank you.
So, colleagues, maybe any question? No question.
Okay, thank you very much in that case.
Thank you for you. So we have wait 1 minute, and I can introduce Vladimir Palulin. Okay.